Good afternoon, everyone, and thank you for joining us today. And today it is our uh, third part of our five-part training series on use of low-cost sensor for air quality monitoring in South Asia. I'm Abhinaya Shekhar, and I work with Health Effects Institute. I take care of the research and the capacity strengthening initiatives that we do in South Asia. Uh, Before I get started with the session, to those that who are not familiar with Health Effects Institute, Health Effects Institute is a non-for-profit research organization that provides impartial science to inform decision that foster a healthier environment for all. And we work on three different verticals: energy, environment, health, and global initiatives. Under our global initiatives program, we are active in regions like South Asia and East Africa. In South Asia, we do a lot of capacity strengthening activities specifically for the early career researchers. In the past, we have conducted a training series on air pollution and health on both in person and virtual mode. And this year, we have planned for a five-part training series on the use of low-cost sensor in South Asia for air quality monitoring, and we had two sessions already completed. So our first session was on the use of low-cost sensor for air quality monitoring. The overview was provided by Dr. Shrikant Vakasala. Like he explained us different types of technologies, advantages, disadvantages, applications of low-cost sensor, and also walked us through different sensor components. And the second section was by Dr. Sophia Rao and Dr. Dio Okure, who explained about the siting and network design criteria for the low-cost sensor. And today's session is on how to maintain and how to set up a large low-cost sensor network. The recordings and the slides of the earlier sessions is available on our website, and I can also share the link with you in the chat box. And for this session, we have Dr. Nimit Godhani with us. He's from IIT Kanpur. So he'll explain us like how to build a working on low-cost sensing technologies, and his research centers on deployment and calibration of low sensor for monitoring particulate matter and trace development of this calibration framework, and also function of sensor with satellite and model outputs. Is very much interested in available cost-effective monitoring solution for across rural and urban regions. He has a PhD from Saurashtra University, and his PhD was on study of atmospheric aerosol and radiative forcing at semi-arid region. And the work that he's currently doing is something which supports micro and macro scale airshed identification, exposure assessment, hotspot mapping, and evidence-based air pollution mitigation. And he was also involved in developing a manual for air quality monitoring using low-cost sensor network, and he'll also go walk us through the manual. We are very glad to have you, Namit, you for this session. Over to you. Thank you for joining us. Yeah.
Okay, thank you, Vinya, for the very nice introductions.
Now I will just start for here. Uh, Mainly, we work on the loco sensor that we have installed over the UP and Bihar for the 1400 sensor. So when we heard the name the loco sensor, what is the loco sensor? So loco sensors are the like basically affordable sensors, compact sensing devices, and which be easily scalable for the dense monitoring or the well deployment is like expensive instruments cannot be feasible. So for it comes in our mind that what they can measure. So they particularly generally now in the whole world recent trends it comes to the low cost sensors. Mostly the people are using the PM2.5 and PM10 sensors. They're based on the me scattering theory, and they are hello hi. So they are actually work on the light scattering principles. There are some other sensors also we are using. There are gas sensors like electrochemical sensors for the gas measurement, like NO2, carbon monoxide, carbon dioxide, ozone, nitrous, and etc. There are some other instruments also that in this area domains that people are using for the temperature, humidity sensors, noise sensors, water quality sensors, soil measurements. And even after the some testings, people are now even in our group we are started to measure some other component of the atmosphere and in the atmosphere.
Nimit, please go ahead.
Nimit is on mute.
Oh,
Okay. Can you hear me? Hello.
Yes, yes.
Yeah. Okay. And this dense network can support the research and public awareness and decision making, like government, non-profits, and other policy making officials to tackle the air pollution at the pinpoint level, that where the pollution is coming, where it affects the most, and how to mitigate the air pollution at the local levels. So, in this case, loco sensor is just a complement for the reference grade monitor. It is not the replacement. Still, we need lots of reference grade monitors to measure the accurate data for the research purpose and calibration purpose to support the loco sensors data even at a large scales. So some of the key characteristics of the loco sensor is like first is anyway you will go like first question come to our minds that it is the price. So typically they will be very few $100 per unit compared to the reference grade instruments which cost thousands of dollars in compared to this loco sensors.
Recording in progress.
These sensors are small, lightweight, easy to carry, and which is very portable. You can set IoT-based applications to see the which area you need the most loco sensor to be installed. You can track the air pollution level live in the mobile application or web application anywhere you want. Uh, there are some criterias also there. They have the lower accuracy than the reference grade monitor, which requires like period time to time calibrations and corrections that directly need to be fed into the motherboard of the instruments. Uh, One other consider we can is earlier I said that can enable the dense monitoring network. I- There are also some like low shorter lifespan. Even the most of the sensors you see on the internet nowadays, they are selling some few dollar prices. You will see the through the data sheet, they will show that our sensors is capable of monitoring for the 5 years, 10 years. Some people are claiming the online there for the business purposes, but actually it is not. This need a quite regular time to time calibrations. Even mostly the in our case we use the highly polluted area, the maximum lifespan is not more than 2 years. We have to replace the sensors for the longer period for every 2 years or something. And these sensors are very like sensitive to environmental conditions like temperature, humidity, dust, corrosion, vibrations, irregular electricity conditions, and everything. So here we can compare the like what is the difference between the low cost sensor and reference grade monitors. So low cost sensor, obviously the price will be the low for the accuracy will be the moderate. The mostly the accuracy will depend on the where you monitoring also. While the reference grade monitor is very high accuracy, you can see the error between less than 5% or 3%. Maintenance is frequently required in the low cost sensors. While in reference grade monitor, you have to check with the mother instrument like in in a year between time. Calibration is essential. While in reference grade monitor, you have to periodic calibration will required from year to year or season to season. By deployment, it's a large number. Obviously, in reference grade monitor, you don't get this much of sensors in very lower price. So that is the limitation of the reference grade monitors. And uses that also I have deployed the dense monitoring and high cost sensor we use for the regulatory compliances for the policy and reference grade monitors. So this is the loco sensor manual we have developed at the IIT Kanpur, and which will help any person, even that from technician to the researcher, which help to how to install, maintain, acquire the data, how to fed the calibration factors into the loco sensors. So it will help each and every person in a easy way to how you can actually measure the PM concentration in a right way with the low cost sensor. So our scope was to for the even researcher, government peoples, even normal public like you and us, other people, they easily can understand. And other was our focus was to like cost effective solutions to provide air quality monitoring, which will be equipped with the individual knowledge, skills engaged in the air quality monitorings. And so overview of the low cost sensors provide real-time measurements. We have in our first deployment, we have used PM 2.5, PM10, relative humidity, temperatures. These four parameters we are measuring. There are quite limitations for the each and every sensors. So in the market, that all over the sensors are monitors, low cost monitors are available. The PM 2.5 ranges are between 0 to 1000 microgram per meter cube, while temperature -10 to +60 degree. If you are living in the extremist area with have the higher temperature or the very lower temperature less than the -10 degree, then we have to move like other sensors also. Relative humidity 0 to 99. So this is one kind of sensor that we have installed in the Uttar Pradesh and Bihar, the IGP region of the India, where you can see the PM10, PM1, PM 2.5, all the parameter we can see. We also enabled some GPS data, battery levels to monitor frequent of this. So this is the our side view of power switch. You can see SD card, power indicators, our whatever IMEI number we used as a device ID to identify the which device is installed at which location, and you can easily can get access to the data. So this is the some installation we have done. We used two type of power supply. We used directly power supply DC in, which will be converted to the requirement by the sensors using the SMPS. While we use the solar panel also, which can helpful to measure the PM concentration over the remote areas for a longer period. This is the RH and temperature sensors combined. So this is the air vent for the PM sensor. This sensor is the inlet. This is the outlet of the sensors. So PM sensors can suck the air from here at the 1.6 liter per LPM flow rate, and it will be out. And in between with the laser scattering me theory, it will measure the PM1, PM 2.5, and PM10 also. So this is the some internal parts that we have used in the sensors. I'm just showing the schematic diagram here only. So this number one is the SMPS for the regulatory power supply. You can easily can access the AC mains, which will convert to the DC 5 volt supply that we required for the motherboard and sensors to run. Other is solar panel. We have also added the battery backup for the emergency power supply, which can now we are getting only 6 to 7 hours of battery backup for when power supply or solar panel not don't work at the night time or somewhere. So we use the somewhere like this is the temperature and humidity sensor. This is the PM sensor that we used. Uh, then we have used also the GPS and GSM. So GPS that we used for the latitude longitude position. Suppose you are traveling with your sensors in any vehicle or mobile laboratory. So each and every coordinate you will get the GPS your locations along with the data sets in the same format. So it will be easy to monitor like across the city or anywhere. So we also added some micro SD card in case of the failure of the network problem or Wi-Fi. It's not network connectivity is not available. So anyway, data will be recorded into the memory card and that will be retrieved for the further analysis. This is the real-time clock. We also have added extra that will provide you the timestamp for the each and every measurement, and also in on the monitor you can see the PM 2.5 and other parameters on the display. So comes to the working principles. So almost and nowadays mostly you all are the from the scientific background. You all know that how the loco sensor works. So once the in inlet the air is passes through the tube at the fixed flow rate. So some wavelength will be some one laser will be bombarded at the uh, area, which will the reflected light will be detected by the detector, and the signals the captured signal will be converted to the PM concentration using the PME theory, and it will be transferred to the processor and saved to the memory. So here we can see one more thing in the laser that we generally most of the sensors which use the 600 to 700 nanometer wavelength. And in this particular sensor that we have used, it has the 660 nanometer wavelength with the full width half maxima FWHM you can call. It's around the 20 nanometer, which is not quite good, because if you are using a particular laser for the detection of a high accuracy, you need a very sharp laser at the fixed wavelength, which will give you a good results, but it will be quite costly for that. But we can also by comparing the kind of instrument with the reference grade monitor, we can adjust the other parameters, and we can correct these sensors and the PM concentrations. So we have for the safety guideline, we have for the sensor, we also developed like a voltage firstly. So in the remote areas or everywhere you go, the now for voltage fluctuations will be the most. So to ensure that voltage should be the very stable. Otherwise, you can add some battery bypass and something like that also. Current, you have to check the data sheet for each and every sensors. Once you connect the your sensor with the motherboard and power supply, because each and every sensor have their voltage and current limitations to the certain levels. So also we need a regulated power supply to avoid fluctuations which could affect the sensor performance. And most important thing is to double check the polarity of the power connections right now, because local sensor now use directly in the wire sheds which have some different connections also. So once we are connecting the sensor, make sure that each and every connection should be right. So ensure that power supply is free from the electrical noise. It will mostly affect the processors and sensor laser to and which will leads to the inaccurate measurement of the particulate matters. And if it possible, use the fuse protections similar to the safeguards. Use appropriate gauge wire, which would be like you shouldn't have to worry about the in the harsh weather conditions about for the power supply to the sensors. And temperature is the most effective parameter for the each and every electronics devices we use. So excessive heat can affect the performance and longevity. So make sure that you cannot put your device directly into the sunlight or very hot area. So there are some you all know that some US EPA criterias for the measurement of the locus sensors. Sorry, be, any air pollution related measurements. There are some Federal Reserve measurement, federal equivalent methods, and the sampling frequency should be the 24-hour averagings. Mostly we are using like 24 hours guideline you see in the any national standards for NAAQS and WHO guideline. You will see like 24 hours mean should be this cutoff and yearly mean should be this cutoffs, and continuous monitoring. So some method allow us to continuous monitoring in the real time collections. So supposedly we used some other like attenuation based method. So it will gives around 15 minutes to half an hour to take one point of data. Instead, this laser based instrument, we can get data from 1 minute to 60-minute in an interval as we whatever we choose. So there is some criteria that we have set like calibrations, regular calibration of the equipment and sensor to maintain the measurement accuracy. Performance, we have to check the periodic performance audit and precision checks. So we are maintaining the logbooks for each and every sensor, which how frequent they have been calibrated at the our validation site. We are validating each and every data sets. Sensitivity, of course, this is the ability to detect the low level of the particulate matter. So it is very highly sensitive to that. Accuracy, in terms of accuracy, the closeness of the measurement is true to the concentrations, but not the actual concentrations. So we have to repeatedly uh, measure the collocate locus sensor with the reference grade monitor and time to time update the correlation factors. Precision, so the consistency of the measurement under the same conditions. So this is the big change in the, like Southeast Asia. We can see in especially in India, you can see very harsh monsoon, winter, and summer seasons are there. So this will also affect the precision of the PM sensors. So for that, we need every seasonal calibration also required, and to affect each and every point of humidity and temperature, we need cross correlation between metrics of temperature and humidity to rely on this PM concentration. So this is our collocation and calibration site at the IIT Kanpur that we have used. So you can see there is some locus sensor that these sensors actually before deporting locus sensor network into the field, we collocate for them 15 to 30 days. Is that, and same kind of sensors from each batch we run continuously for longer period like 1 year 2 year like this. So we can measure that okay, this sensor in our calibration facility has this kind of drift, so what kind of drift will be there into the field. So that we also can identify with this help of this kind of management. And there is some US EPA criteria they have provided, like R score should be zero point 0.7, slope should be like this 1 plus or minus 0.35, intercept -2 plus 5, RMSC should be less than 7 microgram per meter cube, and NMRSC should be less than 30%. So this is our like co-location site at the IIT Kanpur. You can see hundreds of sensors we can co-locate at the same time. We also check the every solar panel, every connections, and every sensor before deployment into the field. Only those sensors demonstrated the good performance into the during the calibration and collocation period. uh, those sensors will be deployed into the field. Other sensors will send back to the factory for the further calibration or replacement of the sensors. So this is some if this is for some of the few plots that I'm just for the visualization I'm giving you, collocations performance evaluation. So you can see we are getting R score around 0.93 and 91, which differs from each and every sensor to sensor. And now you can see we also have around this kind of equations where linear regression equation we have got. So before the deployment for each and every ID, we are this equation we feed into the motherboard of the sensor. So it will adjust the PM concentration according to these equations. So this is some, there is also a very useful thing that we have done before going to the field. Like there are some site selection criteria that how to choose the site, where to place the sensor and where not to. So is for our first condition, no, is there any continuous source nearby like industry or something? This is for only we are doing only for the ambient environment measurement of the PM concentrations. If you want to measure the PM from the industry or continuous other sources like stubble burning, biomass burning, so you also can put the sensor nearby to the location on the downwind or accordingly, but it should be some far, not exact near to the locations of the burning or source. So in this term, we use the continuous source nearby. Then if yes, then no, site is not selected. If continuous source is not there, then we set some checklist we made. So site is selected for the ambient environment. Minimum checklist should be there, like 24/7 electricity should be there, unobstructed airflow, Wi-Fi or cellular availability, easy to accessible. So these are the some minimum checklist. So when we required, so easy accessible is in terms of that if when we need or when we go for the further instruction or calibration or replacement in maintenance, so there will be easily available to the accessible to each and every technicians or person who is going there. Then if we met this criteria, then we select this site. Yes, okay, this site will be selected for the installation of the device and otherwise not. So this device that we have installed in the field, so this is the installation. So we are installing the devices on the rooftop of the buildings, terraces, balconies, buildings or community centers. So minimum criteria of this is there. You can see that we mounted the pole, this sensor on the pole, and you can see there is unobstructed airflow. So you can easily measure the uh, true ambient air pollution level with the uh, this local sensor. So there should be a 270-degree at least unobstructed air blow should be there. If it is not meeting this criteria, then this should be not less than 180 degrees. So you can directly, suppose you are in the office building or somewhere outside your building, you can place this sensor onto the whole of the any office. This will help you also, but there should be some criteria should match that there is at least 180-degree unobstructed airflow should be available for the true measurement. And the monitor should be placed at the 6 feet above the ground level for the better representation of the exposure at the breathing level zone. It is quietly standard criteria researchers used, but we can use like on terrace, rooftop also you can put it. So some of the cautions that we shouldn't keep in mind that the device should be protected from direct rain, because it is ultimately it's a electronics device, so it would be no matter what you do, but somehow it will has some effect of the water damages and kind of things. The monitor must be shielded from the rain, but it also be sufficiently exposed to the atmosphere to obtain the useful readings. So in this case, we are suppose this box that we have installed, it is already a waterproof and rainproof box. But you can see that earlier I show you there is air vent is required for the inlet of the PM concentration. So you cannot hide those part, block those parts. So for that we need a overshield on that, and the ambient sensors inlet without any interference. So suppose this sensor we have installed here in the this picture you can see, but this sensor you cannot put here because it will obstruct the airflow anyway. So there is the checklist for the device installation. When we go to the device installation into the field, earlier that I show you the how we are selecting the site. After the site selection, we have made another checklist how to device check, like, so check the AC remains power supply. It should be like for Indian standard we are using from 220 to 240 volt AC. Check the DC power supply from the solar panel, which we mostly use that around 12 volts. Proper connections should be there from with respective sockets. So there are some other power supplies, solar, battery, mains. So make sure that each and every connection goes to the proper sockets. Turn on the devices. It will check the LEDs and power connections. Check the Wi-Fi and cellular signal. Check whether data is also recorded on the SD card. So what we do in the this case, we also plug some when we install the device, we go to the field, we install the device, and after there you can live check the in mobile application or web application. We can see the data is transmitting in the real time or not, and then we plug out uh, the SIM card or Wi-Fi from the motherboard, turn off the Wi-Fi. Then the data will also parallelly recorded into the SD cards. So after few minutes, we remove the SD card, plug into the laptop and check. Okay, this data will be now also recorded into SD cards. So we resume this as earlier it was there, and install the device as described above and on the prefix location. Check if the data is correctly transmitted on the server via internet, and the real-time PM, RH, and temperature can be seen on the dashboard. So we also have developed our dashboard where you can see each and every data set of which are updating at every minute, 1 minute interval. So when the data is not transmitted to the server, or if any error comes in mind, so please we make sure that each and every step should be repetitively followed, and unless and until the data in true format is not transmitted, we repeat this format for a few times.
Nimit, before we go to the next slide, there is one question relevant for about what we're talking. How often you need to recalibrate the sensor, and will there be a drift over time? And also, there's other question third question on that, like how do we keep a sensor at a constant temperature?
Yeah, see, the first two question I will answer. I also added this that part drift and other in the later in this lecture. Regarding the sensor, so it won't be possible to keep constant temperature into the inside the box. So we mostly what we do that it we put into the shadow of the solar panel or somewhere that have a minimum effect of the temperature. So as you know that according to the light scattering principle, if the internal or sensor laser temperature internal temperature goes up to more than 45, then it start affecting the most. Below that there is error should be rise, but it's negligible. We can put aside like that. We can ignore also. We can ignore that. So it is not possible to like have same temperature for each and every time. Temperature will be like a regular our cycle in diurnal cycle, that whatever we are using, that temperature will be the same only.
Okay. So how often do we need to recalibrate a sensor?
Okay, so for that, the earlier that I show the some sensors that we put for a longer period, in our
Mhm.
calibration sites. For there, those sensor also calibrated for each and every season. So in India, we use for summer, winter, monsoon, and post-monsoon seasons. And each and every time, we used some different algorithm we are improving our algorithm to match the exact concentration to the reference grade monitor, and then we deployed those equations to the each and every device's motherboard. We can install that firmware. We are updating the firmware for the uh, seasonal basis.
Thank you. There is one more question. So, in case of sensor detection, how sharp is that for the PM1 size cutoff? Because, yeah, for the particles which is near that 1 micrometer, like it get categorized either under PM 2.5 or PM1. So, how sharp is the cutoff when we measure particles of very lower size range?
Mostly you can see that people are saying that okay, this much of loco sensors is our sensor loco sensor is capable of monitoring PM1, PM 2.5, and PM10 also. So mostly it will the 660 nanometer wavelength that they are used from the Me theory, and they are calibrating those sensors, which is give you the accurate result of the PM 2.5, but not the PM10 and PM1. PM10, PM1 is also a very small fine particulate to measure for the local sensors. Anyway, it is giving some idea about the trends, but it is not the actual results. So if anybody claims that we are using the local sensor in that, they have to double check the results. And we also have seen the some installation that we can see that almost like 5 to 7% or 10% PM10 concentration is higher than the PM 2.5. In actual case, atmosphere don't behave like that. So there is some discrepancies from region to region, and each and every climatic zone. So they have the other criterias. Suppose we check the in northern India, like a biggest city like Kanpur, Lucknow, and Delhi, we are seeing that the PM10 concentration is almost double or more than 200% in terms of concentration. While you measure with the local sensor, it will show you around 20 to 30% higher. So for PM1 or PM10, we are making sure that this should be very less kind of thing.
Mhm. Thank you, Nimit. So Ronald has a question. Ronald, can you unmute yourself and ask like the question was on like does the sensor do basic edge processing?
Yes, age processing. Yes, they do.
Okay. Okay, you can go ahead. Nimit.
Yeah, okay. This is simply, I'm not going to about data analytics part. So this is like our sensor. We use after the calibration, we fill deployment data from device with ID and timestamp, which we store as a raw data, as a level 0 data sets. We archive those data. Then after we perform the QA/QC as per the limitations, we have performed some sudden spike removals. Then we save those data sets as the level 1 data sets. Another this data will be archived, and further from archive the we you can use that data as a scientific analysis, data visualization, scientific reports, policy making, and etc. So in troubleshooting and maintenance, so there are mainly few things. The dashboard, our dashboard is provide the real-time data, allowing user to see the sensor continuously. A user can identify and flag the sensor that malfunctions and directly through the dashboard interface. So what we do is that if any sensor does not give the proper reading for at least 72 hours, then we flag those sensor as a malfunctioned sensor, and we send our technicians to check on the site, and we process as the earlier checklist. We repair or make some difference or replace the sensor, and then we restart those sensors. And faulty sensors with an inappropriate also will be replaced with the new sensors. So we keep stocks of the new sensors only, not whole monitor. We are changing only sensors. So this sensor will be replaced with the new one sensor. Mostly the low-cost sensor have a lot short lifespan. The accurate measurement it's very limited than it's claimed by the manufacturer. So in these projects, in our we are replacing the new sensor after 1 year or 2 year of the field measurement from the date of installation. So suppose we have categorized these sensors in like uh, three zones, three cases. Like if device is not working, so we dismantle the device, take a new sensor, connect the sensor to the device. Uh, we place the new sensor. Inlet and outlet of the sensor should properly place the lock nut opening, and repeat this checklist for the device installation earlier I showed, and cleaning the device. So on the right side of the device that I showed you, the uh, uh, two air vent was there. So we blow some air and clean the sensors also. If it is working continuously for the matching previous results, then we keep it that way. Otherwise, we will change the sensors. We also clean the solar panel time to time for the better power efficiency. If data is not being transmitted, so if battery is 0%, we also transmit the battery percentage of in logs of each and every readings. So if the battery is 0% in the last transmitted data, it means the device is not getting power. So we send someone, we double check the power, and make sure unless and until uh, monitor comes online, we will check, and then if the data comes, monitor comes back online, then we marked it that marked as a case is resolved. So if a device is on and still data is not transmitted, so we dismantle the device there. Once we remove the SIM card, and we just like that we in our mobile phone that we use like aeroplane mode we using. So in the similar way, in the modem, we use there is a kill switch in the modem, so we use like for SIM card to get a better network, and that will be data will be transmitted after few minutes. So there is a third step also, that when we are check the SIM card, and if Wi-Fi is not available, if our sensor is works on the Wi-Fi, so we also turn off and turn on the Wi-Fi, and we also check the strength of the Wi-Fi using our mobile phone also. In case of the SIM card, we especially for M2M SIM also check the APN settings, check the roaming is turned on. We put the SIM back into the slot and ensure it's not loose. And this still does not work, try to replace the SIM card and see if that works. And if still device is not working, so after that we trying to change the location of the device for the better connectivity. And we also check the antenna to be tight in the holder for the red PCB. Some other issues is also there. So device is connected, but data is not showing on the display. This means there is some wire connections is also loose, or this kind of thing problem also will come time to time. So we dismantle the device, open the device, switch on, switch off the device. Unless and until the power don't come, we also check the SMPS and main lines power with the multimeter and internal strip into the SMPS. We also check the wire found it's okay. Then uh, if there is some issue in the sockets, we are also replacing the sockets. And power supply issue, we are using if some wire will be damaged into the field, so we are replacing with the new wires and other things. So some accessories that will required also for the installation team. So when we send our technician into the field for the uh, like maintenance or routine maintenance or troubleshooting, so we are make sure that this kind of devices should be with them. So then no need to worry at the time of installation. So they will carry mostly laptop and multimeter. They are the must priority. So they will check the power supply, their sensors and laptop for the connectivity and for recorded measurement into the SIM card. So this is the overview of our application that they have developed the application. You can register with your email ID or login. Then you can manage your sensor from here. So here, suppose if you have, you can from by adding manage, you can add your sensor. So when you purchase a sensor, they will give you a unique ID like that I showed you earlier that it is V same as the IMEI ID. So that will you can add here after the authentication. You can see where your sensor is placed based on our GPS location. So you can here you can see that okay, this sensor will be located at this place. If you have installed multiple multiple sensors over a different location, so you can search your ID, device ID from here, and you can see the results like this from each and every device. So this is the temperature and humidity and PM concentration. You can also feed directly calibration factors using the device IP. So drift detection and analysis, the when earlier that you are asking the question. So what is the sensor drift in the low-cost sensors? So sensor drift is like a gradual changes in the sensor's output over a time, uh, even when the actual pollution level remains the same. As a result, the sensor may starts giving a higher or lower readings than the true value. So often we have noticed that there when after a longer period, without entering any seasonal calibration factor, if you measure the PM concentration for a longer time, it will show some drift into the measurements. So for that, we used other algorithms to detect the drift and aging of the sensor. So why drift occurs? So aging of the sensors and components. So as you all know that generally the laser is like a light source. So after time to time, this sharp laser source will like start to decompose or have the decreased its intensity. Or you can say that if in loco sensor we used like which has the FWHM, which is 20 nanometers. So after a longer period of use, it will increase to 30 or 40 nanometer in wavelength. So it will also affect in the calculation of the PM concentration using B theory. So it is a very tricky part, and we also have to measure those things also. Effect of the temperature and humidity we all know. dust, moisture, and chemical contaminations. We all know that all kind of chemicals and other pollutants will be into the atmosphere, will affect the sensor. Sometimes it also deposit on the detectors also. So detection capability of the detector will decrease, and it will give you the like inaccurate results. Power supply and electronics degradation, that this power supply and electronics degradation, it's a very not usual thing. But yeah, first 4 point, it's the most common things that we noticed in our network. So type of the drift is there, like first is the baseline drift. So sensor shows non-zero readings even in the clean air. So we did some one experiment in our lab, that we put very clean room, in a very clean room. Uh, we put some one reference grade monitor and one local sensor in the closed chamber experiment. So it will still gives the higher concentration, or even the then 3 times, 4 times higher than the reference grade monitors. So this shows the baseline drift, we can call it. The sensitivity drift is like a sensor response become weaker or stronger over the time. So yeah, drift detail. So yes, you can see here that okay, for the lower time of period, you can see here the PM concentration is matching for hourly data. But after some time or some fall, it you can see there is a we here also data will also was there, but in our analysis in the screening method and QAQC method, it was removed. After that, we can see that okay, this data set, after some time, this data is not matching with the reference grade monitors, and we can see there is a very lots of discrepancies, and trend is also not matching. So we can say that okay, this sensor has now some kind of issue, internal issue, aging or drifting is there. So this is that one interesting figure that I found in that that each and every angle of the scattering, you can see there is an intensity, arbitrary intensity. It's changing over a particle size also. So after intensity is also decreased over a period of time, then or your particle size is also measured wrongly. So here we used some one technique for a drift detection and analysis, and we also corrected. So we used some one LSTM plus XGBoost method to accurate fit accurately with the original results. So earlier I show you in this mean period, like here in this, after this period, one we can see that there is a lots of drift was there, but after uh, adding this machine learning method, we can you can see that the drift is almost become as earlier, and it's giving almost true values. But my suggestion is that after 1 or 2 years, we shouldn't continue with the low cost sensors. We should replace them. So in this case, we improved our R score from 0.76 to 87. So we have predicted the error of magnitude over the time. So this is the chart you can see. So uh, this is the iterative process for anomaly detection in low cost sensor. So we take corrective actions, calibrate sensor data, use calibrated data for prediction, analyze, set anomaly threshold, and detect the anomalies. So these cycles will be like a snake tail eating kind of process. So you have to keep it continuously for repetitive process. And after the deployment, you can see once suppose this is the dense one of this is only one state that we have installed so many sensors. So how you can like calibrate entire network. So this is the big challenge, you know. So when we detect this kind of things, so what we do, we have the government monitor. Suppose this HCS blue dots you can see, there are many more. There are only mostly 35 reference grade monitor across the state. We put one device along with the reference grade monitor into the field also. So from that we are measuring that, okay, this drift or these sensors have this much of drift, so nearby sensors or entire area compared to the those 35 sensors, how much errors is there and how much calibration we needed. So for that we are using one like calibration method using deep neural network. So this we have submitted in IEEE sensors, is now under review. So this now I'll go over the Amrit loco sensor network by the IIT Kanpur. So some outcome. So this is the government.
Before we get started with this case study, there is one question by Revan. So, in case of co-location and calibrations, are there any equations for differences in because
Yes,
factors like temperature and relative humidity should also be considered while doing that. So, can you
yes,
talk
yes.
about the equation? Yeah.
Yes, okay. So, yeah, so what we do is that earlier that so the long for the longer period sensors, we take the data from even we also have the temperature for temperature and humidity. Vaishala instrument is there for the reference. So what we do is there we compare the temperature and humidity also. We first correct the temperature and humidity by point to point measurement with good quite good results. And then what we do is that for each and every uh, point of 1 degree of temperature and 3 degree or 2 degree of the percentage of the 2 or 3 degree of the humidity, we put some intervals and we made a correlation matrix. So for each and every this correlation matrix, we calculate that, okay, if humid after some period, humidity and temperature criteria should match between those range, then the equation should be this. So in that way, we are calibrating the seasonal calibrations also for a longer period.
Okay, and there was also another question I think you've already mentioned during the talk. What is the range of, like, I mean, the measure lower detection limit of your sensor? I think.
Okay, so in lower detection range is like 0 to 1000 microgram we will generally know, but thing is that it in terms of conditions when you in like a very clean room you also measure the PM concentration, it will give you some range between not actually which is the PM, it is not actually there. So lower detection, we mostly measure above the 3 or 5 microgram per meter cube in the low side. Also, that one thing that I want to mention that in this highly polluted region, uh, they have the different kind of calibration factor for the different range. Suppose if your PM concentration is varying from 0 to 200, then some kind of is there, 200 to 300, then the other code will be also be there. So now we are working on that also, because sometime what happened that you can see that humidity affects the most. So there is one criteria that we seeing that more than 75% humidity. When you measure the, suppose in reference grade monitor we are using EBAM now. So in EBAM works on the attenuation principles. So when the humidity increases more than 80, 85 or 90 uh, before, just before the like monsoon season or rainy seasons, it will shows the negative results, or less concentration than the actual concentration. While in the low cost sensor, the refractive indexes will be changed and it is increased. And that's why even in the higher humidity range, it will show the higher PM concentration than the actual PM concentration. So this is something that we are now tackling between this range. Uh, yeah, go ahead if you have any question.
Yeah, the question is on the next case study, like that something that you mentioned on the Bihar low-cost sensor network. Where are these? Is the data openly available on any platforms?
Yes, data will be available shortly. So we have
Okay.
put our public we are managed our new with the high capability servers, and we are launching one event went in December. So some data will made public, and entire network data will be made public shortly.
Thank you. You can go on.
So,
Thank you.
yeah, okay. So you can see the red dots are the government or reference grade monitors. So you can see they are very sparsely divided, and they have the hundred of kilometers distance between two sensors. So in between that, what is happening, nobody knows. Where it is pollutions is sources, nobody knows. So for that, we fill this gap, and in entire area, each and every block level, we have installed the local sensors, and you can see the map how dense network we have created in these two states. From this outcome, we have defined like one data-driven airshed, micro and macro airshed that we use some PM 2.5 data, meteorology, machine learning, and to derive the airshed. So this is our local sensor meteorological data from grid, other topographical data, boundary layer, air temperature, surface temperature, and everything. We use the ventilation coefficient also. We feed in each and every our data using LSTM, and then output will be in the embedding layers in the vector format. And then we perform the hierarchical clustering, and we found the 5 different airshed in the Bihar. Earlier, there were some paper were published, some other journals. They shows the entire IGP region, including from the Delhi NCR to the border of the West Bengal, as a single airshed. But this is not the case here. You can also see the micro airshed. So this is, you can see each and every season there is a micro airshed is going over. Uh, Season wise also there are some drift, and boundaries will change on season to season, but mostly they will stay in the same region. And we have also identified in our next work, we are also identify that which sources it's affecting the most to form this kind of airshed. So this is the more 5 year shed. So actually this figure kind of demonstration we gave to the government authorities to for which region people have to focus to control the air pollution. And clearly you can see, suppose you can see in seasonal differences, you can see vast difference between airshed 1 and airshed 5. So it's like around 200, 300 in the winter. It's a seasonal mean is going more than 200. Here you can see level around 120, 130. So there is a huge difference between the different airshed air pollution zones and their air pollution levels. So this is how each and every district wise we have also put PM concentrations. So we give this data to the authorities, and they will make sure that next time they will make a policy to intervene the pollution. So this will be helpful to them. So another case study we have used did this like air pollution exposure assessment. This paper is we are in a communication now. So our PM 2.5 data we are processing. We used 500 by 500 meter different 54 variable, including meteorological variable, land use, land cover, geographical, and other variables. We train and test the data. We use gradient boosting regression model and random forest. And this will give us a high resolution PM 2.5 prediction at 8 hours interval. So we can create an entire time series of the PM 2.5 prediction at 500 by 500 meter grid, which has a good accuracy. I can say that we matched with the actual measurement of the PM nearby PM sensors, which allows us to more than our score is more than 0.76, while with the nearby or in pinpoint, it's going up more than 0.87. From this map, you can also identify the hotspot. Where are the hotspots are there? Where the air pollution is over the time to time. So this is we are predicting at 8 hour intervals. So it means that we also can identify the which region has the permanent hotspot. So we can identify those regions and we can take a action for the further implementations. And we did exposure mapping as like what kind of asthma and COPD and what kind of how many deaths will be reported in the this period. And so in this we did the short-term exposure assessment. So this is the one plot that just for the visualization I'm showing that populated waste rate concentration we did for each and every village level. So you can see the PM concentration that we have assigned PWC to the each and every village. And clearly you can see the difference between the Bihar, the northern Bihar and southern Bihar, that there is a quite difference between in the total due to the geography and the what populations and everything. Another case study we did in the Lucknow, that in Lucknow you can see we did a whole district. We deployed 78 sensor in the single district. We made this using the visible satellite imagery, and we identified the hotspot in this very Lucknow city. So this box will be zoomed out here. You can see this hotspot at 500 by 500 meter grid. So here some bricklines plant in outer periphery of the Lucknow city, and this is the very our Talkatora industrial area, and this is the central zone of the city. So you can see the higher air pollutions there during the season. So we use this local sensor to help the policy makers, like the regional coordinations. Airshed frameworks will enable the multi-jurisdictional collaborations for the pollution control measuring the targeting shared atmosphere basins. So in that case, what happens? Suppose we see that nowadays we are seeing the transboundary air pollutions. So for that, each and every jurisdiction has come together and take a action to mitigate the air pollution. So for that, this kind of dense network will help very much. Targeted interventions. So we have the high resolution data, we have identified the hotspot, which will help to take require immediate actions, optimizing the source allocation for the maximum input. Uh, and third is the evidence-based regulations. So now till date, what was there? So, the policy is made by the policy makers, which was like same for the whole region or whole country. But here we are giving them evidence. Okay, okay, this particular area we need to more focus to mitigate the air pollutions, and this will help very effectively uh, to mitigate the air pollution. That is my suggestions actually. So thank you, everybody. That was from my side. Any question, if you have, you can ask freely.
Thank you so much, Nimit. That was really a wonderful presentation. I think I could go back to my engineering classes. You covered almost everything. We have a question from Ash. Ash, can you unmute yourself and ask?
Yeah, thank you. Thank you so much for the awesome presentation, Nimit. I
Yeah.
was wondering if would it be possible to share those airshed level shape files for UP and Bihar from your paper?
Uh, I will check the. We have only the locations and we have latitude, longitude for the each and every our monitor that we have described in derived into the airshed. But
I
you can
see.
see the figure also, and if it is possible, I'll share. You just drop your email address to Avinya. She will share with me.
Great, great. Thank you so much.
Yeah.
Thank you, Nimit. Do we
Yeah.
have any? Yeah, we have a question. Yeah. Any other questions? Anyone can unmute yourself and ask your question.
Hi. Thank you,
Um,
Nimit. Can you please repeat once again regarding the regarding PM1 and PM10, why local sector is
um,
able to record this kind of
Mayank, I think we can't hear you.
hello? Am I
Y-
audible?
y- No, we can't hear you. Can
Am I
you?
audible?
No, still your voice is losing, I think.
Okay.
Maybe
Can
can
you,
you? Can you use the chat box instead? We couldn't hear you.
hello?
Yeah, that would
Yeah,
be better.
it's better now. Go ahead, Mayank. So, before Mayank fixes his audio, is there any other? So, Rivan has a question. Can you mention the problem regarding PM1 and PM10, like maybe measuring the
Yeah.
particles, the lower size range and the higher size
Yeah,
range?
actually, what happened in the low cost sensor, there is only one detector. You see, if you open the low cost sensor, there will be only one laser source, and that there will be a one direct detector. There will be only no reflector. So what happened when the particle interacts with the laser light, it don't lose their entire energy. So that light that measured by the detector, it's very differ from the actual particle that should be there. So whatever the change in the wavelength should be detected by the detector, it changes entirely. So for the smaller particle and the higher particle range for the PM like PM10 particles, there is a very drift going on between particle sizes. So there is a very there is no differentiations people are now going on. Uh, if you want to see the correct PM1 and PM10 measurement, so since when I also operated the one high cost like laser source kind of instrument, which made I think it was Grim. So for Grim has a two or three reflectors and two detectors. So it will cover the entire area of the reflected light, and that signal will be converted to the PM concentration accordingly. So this is the difference between the low cost and high cost PM sensor in that terms, in the similar working principle of instrument.
Thank you. Mayank, were you able to fix your audio? No.
He just can drop a message
Yeah.
also. Mm.
Do we have any other questions? So, I I just have one question, Nimit, to you. So, to build such a large network across state, across Bihar, how long did it take for you? Like, how long was that in terms of
Then
duration?
it's a very hard to answer that questions. We initially in initial phase we we had a lots of trouble. Each and every batch, we are going hundreds of sensors, managing each and every sensors for 30 days. We have to look, plot, observe each and every data points. Even after we did the programming, also we are generating the lots of data sets. So visually also we have to say, as I show you the time series. So we also compared hourly to hourly time series also, and we have checked those for minutes to staring at the single figure. So each and every day, for the first 3 or 4 months, it's take a lots of efforts. But after the deployment, it was very easy to maintain. Our technicians were also very good at their job, so they did good work in the field also.
Great. And Ronald has a question like, who's the manufacturer of your sensor hardware like that you're using? Was your in-house?
Uh, Actually, in the Lucknow case, we have used Purple Air, and one we have uh, from our side we also developed, so that we used the Purple Air, that Alpha Sense. Now, in last days, we also have used Sensorion SPS 30.
May I ask one question?
Yes, yes,
This is
yes. Go ahead. Go ahead, Karan.
this is Kamran, Dr. Kamran from Pakistan, and thank you very much for arranging such a nice and explanatory lectures. It gives us, at least to me, it gives a very clear picture that what I have learned 2 years back and what was actually missing. So thank you very much for the first. And second is, one thing I wanted to identify is that how big your team is and what kind of people are working in the team, so that if I am planning to, establish such a
Yeah, so in that case, we have our different things from different persons from the different backgrounds. So actually, my background is from the physics. So I did lots of with lots of for a hobbying also. I did a lots of thing in the electronics and everything, signal processing. In myself also, I have. For offline, I have developed a dashboard, so it's just for a hobby, and then I learned a lot. After that PhD, so we also made one kind of loco sensor using like a NOAA sensor that you might heard of. So in the put it in a display, and we have some like a picture. So in that case, I have did, and after that, uh, like uh, uh, one guy in our team was from the like a civil engineering and environmental engineering background. So he helped us to identify the sites where to put the sensors. So this kind of things where he was looking for. One other guy was in our team was from the like a emission inventory he had done. So he helped those kind of inputs into the research area, kind of thing. So my main work was to deliver those sensors on time, maintain those network, keep the data up to date, manage the calibration from time to time and everything. So mostly this kind of thing we have done.
Actually, I am a chemist here, and my whole research is on air quality. So I
Okay.
was wondering that how I'm going to manage a team and what kind of people I should engage with. That's why I asked this, because
Yeah. So,
the specialty you have, I don't have such specialities. But
so actually,
nevertheless,
there is
so
no
please.
need, there is no need for speciality for anything. So if you have kind of interests, you can learn in easy way. So I learned a lot from first when I joined is this project. So I was thinking like, okay, this is very big for me. I couldn't handle it. But after some time, I enjoyed it. So I took it as a
Right.
challenge and I enjoyed it and I learned a lot in 2 years. So So here I can share you. So this is if you can see. So this is the when I was in my PhD time. So you can see this is the sensor that we have developed. So this actually not a mobile. Even if you we are showing for visibly we are saying that PM concentration we like that into the visible display like this. This also takes a lots of effort. So we did some Arduino and Raspberry Pi and those things. So this kind of things,
Right.
these sensors, and we put these circuits boards that we have designed here ourselves here in laboratory for the testing purpose. And yeah, so you also can do this, start from this and learn a lot like yourself.
I will, inshallah. And thank you very much for explaining in such an easier manner that all the gaps has been filled. Thank you very much.
Okay, thank you everybody.
Thank you, Nimit. I think Shrikant is here. So, Shrikant, would you like to answer Karam Khan's question on different specializations? Like that would be required to have a like to build such a, because he's very much actually the reason for having this low cost training, the idea behind having this training series came from him. Like Mohammed wanted to have a training on low cost sensors. So that is how this ideas bro. We had a session on this. So like he's planning to build such a network in Pakistan. So do you have any suggestions for this question, Shrikant?
Thank you, Abhinaya. Like, see, to answer the professor's question, we need a mix of expertise. Okay, basically, on the field, we need field guys. Okay, first thing is we need more field guys because, as Nimit said, the sensors are having a lifetime. After that, they degrade. Okay, suppose if you want to build a sensor network of suppose 1,000 sensors or 500 sensors, and if you take almost a year to build the network. By the time you install the last sensor, the first sensor will be already 1 year old. Its
Yes, yes,
performance
yes.
already compromised. Okay, that's why you need to plan it such that you can complete the installation in at least one season. Okay, that's how you need to fix the time first. Then you need field people, and mostly what expertise required is some smart field people who should be able to see. And the host part is very tricky. It all depends upon where you are going to install. If it is on government buildings or if it is some residential areas. If it is a residential area, if you are trying to put a sensor in somebody's rooftop or terrace, then it is very challenging to convince the host. Okay, you need to tell them that this is not a CCTV camera. This doesn't consume much of electricity. Your electricity bill will not increase. If you are having a solar panel, that's fine. Otherwise, if you are tapping power, then if you are tapping Wi-Fi, this is some smart field people are important, first thing. And second thing is, based on the number of devices, then you need to have these many field people. At the same
Yeah.
time, suppose if we are doing in a different places where you have a different language constraint. Suppose I speak a different language, and if I'm installing in some other state where it's a different language, then again the local people makes a difference. And another thing is, on the lab side, you need to have this calibration setup. Mostly, we need some people who are having experience with this low cost sensor data analytics to continuously monitor whether the data is giving you right values or not, or whether it is correlating with the reference grade instruments. Basically, we need to check the uh, accuracy of the sensors. At the same time, we need laboratory experiments like for the field, sorry, for the co-location. You are deploying hundreds of sensors at a time with the high-end instruments. You need people who can operate these sensors at the same time, the high-end instruments. We generally see Nimit kind of people, they have done their PhD in this field of science. That's why they can easily operate. But if you are starting this whole setup, then you need people who has expertise with the aerosol instrumentation, both high-end and low cost.
Yes,
And
yes, definitely.
you need people who know instrumentation. You need people who has soft skills, like you need to continuously evaluate your data sets, and these instruments generally throw you huge amount of data. you can always you need always some people who are good at coding. Okay, some instruments give very sparse data you can handle in Excel sheet, but these low cost sensors, these many sensors with high resolution data sets, you need people with soft skills, and at the field end you need smart field people to complete the installation quickly. This is how I can put it, and this is what you need, and it all depends upon your numbers, at what numbers you are looking at. And what I can say is you should deploy it as quickly as possible, such that that aging effect doesn't kicks in by the time you install the last sensor.
Yeah.
Yeah, thank you, Shrikant. Nimit, you have any final remarks before we conclude?
Oh, it's great to me that I can give my opinion that I'm happy that someone can learn what I have learned in 2 or 3 years, maybe it's around 3 years. So yes, and Shrikant was very he was very right in that way that we need lots of team. In my team, we was three postdocs were there, and we have four engineers in the time when they are going to the field. So they were standby positions that okay, this sensor goes offline, we tell them, he immediately rushed to the locations, or they did lots of traveling. So did take very quite a lot of efforts to manage this kind of network. So
Yeah.
yes, that.
Thank you so much, Namit. I think the data that you people are generating will also be very useful for us to understand how the equality is changing in the state. And we are looking forward to the data when it comes out to the public. And thank you so much for joining us today for this excellent presentation. And I thank all the participants for joining us today. Our next session on data management and analysis is scheduled for February 10th. See you all there. Thank you.
Thank you, everybody.